Okay, welcome back to the second part on bit manipulation. What we are going to do now is build on top of the theory we looked at yesterday and few examples, and we are going to now take a look at the practical aspects of how to go about doing bit manipulation. Okay, so this is what we looked at yesterday. Uh, Let me put myself up here. And this is what we looked at. We looked at and represented with this or represented with a vertical line, a single vertical line. Then we looked at the XOR using the caret symbol or the power of symbol. And then we looked at not, also called inversion. And then we went on to looking at, the left shift, two arrows, the angular brackets, two of them are pointing to the left and two of them pointing to the right. We said that was the right shift operator. What we'll now do is start off this with this and this, which is the shift operators. And then we'll kind of, add more and more layers to it. And of course, along the way, I'll explain as to, how, let's say, the open source or Linux community or the systems community uses these. Okay, so first off, let me get myself out of the way. Then let's open up the main.c file, and this is what we had. Okay, this time around, what I'm going to do is we're going to look at the shift operators first, the left and the right shift. And I'm wanting to kind of take out of the way one special behavior that happens with the unsigned, sorry, I take that back. One special kind of behavior of the signed numbers when you perform right shift operation on those. So let me take a number, let's say A, and A is simply 1. Okay, perfect. And note that, A is signed and A is 4 bytes. And A is 4 bytes because as per the previous video, the part 1 of this bit manipulation series, so int on my machine is 4 bytes. Int on any 32-bit machine can be safely assumed to be 4 bytes. Okay, so let's then play around with this. So first let's talk about, and we're going to use printf a lot. And what happens is, and by the way, we are also going to use the %x, which is for printing numbers in hex. So that makes life easy. So what I'm going to do now is shift A by 31, right? And just as a quick reminder, we yesterday looked at this, that if we have 32-bit integer, what that means is we have places 31 down to 0. So 0 being the LSB bit and 31 being the MSB bit. Fair. So what I'm essentially doing is I'm taking 1, which is at this LSB position. Why is it at LSB position? Because, hey, 2 to the power 0 is 1. So 1 is represented by putting or turning on the binary bit at the 0th position. Then what I'm doing is saying, hey, move it to the 31st location. Right? These were 32 positions in total. I'm saying, hey, the first position is taken. Now take this, whatever the bit pattern is, which happens to be 1, and on the left all zeros, and I'm saying, okay, push this by 31 bit positions. So 1 comes here, then here, then here, so on and so forth. After 31 hops, it comes here. Okay, so first thing is I'm moving it to the left by 31. One other thing to remember is A is a signed number, right? And it is a signed number because, well, we don't have unsigned integer here. We do not have this. We're saying, hey, take A to be an integer. Integer means that it's a signed int. Actually, int means it's a signed integer. Unsigned int would mean, hey, it's not a signed integer. Okay, perfect. So what I'm now going to do is print the value of A as decimal also. So let's do this. A in hex and A, or actually, let's do this. Decimal, right? And to print it in decimal, I simply use slash %d slash n, and I'm going to just repeat the same thing. Okay, perfect. Let me write quit. Let's do gcc main.c a.out. Now, what do we expect? Let's see, let's make some predictions. So given 32 bits, we moved one from 0th position to 31st position. And notice that the 31st position is a signed bit. And this is what we talked about yesterday. In 2's complement form, the signed numbers are stored with the MSB representing the highest negative value. So it's treated as something like so, right? So what we should then see is the %d part should represent or should print a negative number, and the %x part should print something like, let me put myself here, 8 0 0 0 0 0 0 0. So 1 byte, 2 byte, 3 byte, 4 byte. In the 4th byte, we have 4 zeros, expanding this out, and then we have 1 0 0. So this makes it 8, this makes it 0. So we have 8 0 followed by all of this. So in hex, there's no positive and negative numbers, it's just hex number, right? So it'll just represent the bit pattern as hex number, and the second one, the %d, will actually represent the signed value. All right, do you see this? So the first one prints 8 0 0 0 0 0 0 0 as expected, and the second one prints a huge value. This is the highest negative it can get, a 4-byte int. Well, highest in the sense, highest negativeness, which is the lowest integer number that it can become, is this. Great. So why am I emphasizing on all of this? Okay. And this is where, now what I'll do is kind of going to blow your mind, most likely, if you're not familiar with C code and bit shift operators, this should blow your mind. Now what we're going to do is we're going to say, hey, A is moved to the left by 31, and then we are going to move the 31st bit back by 4 position. Okay, so let's do this and do kind of, record what you expect. And whatever you see now will be a very special behavior that only happens for signed numbers. Okay, so let's do this. I first move A to the left by 31, which makes it the least negative it can get, and then I'm moving it to the right by 4. And the behavior you see, my claim is, will be a very special behavior of signed numbers. And let me write hex here. Okay. Save the file, compile the file, and run the file. Okay. What do you observe here? Notice this. And let me pull myself here. Isn't this strange? And if you're not yet in awe of what happened, well, we had 32 bits, 4 bytes, signed number, 1 was here. We moved it all the way to the end. Fair? So 0 0 0 0, all the zeros, that is what we see here. We printed that as a decimal value, so it turns out to be the lowest negative number that we can get in 4 bytes. And then what I did was essentially took this thing, which is A left shift by 31, This is the result. So 1 with all zeros on the right, all 31 zeros on the right. And I said, hey, move this by 4. So, move, 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 right? 1 move, 2 move, 3 move, 4 move. So we should have gotten something which is like this. That is what anyone in their natural state would expect, saying, hey, we are moving 1 to the right, so this position here will be filled by zeros. But yesterday we talked about that in case of a signed number, what happens is whatever is the MSB, that will get replicated. And if you notice, that is what has happened. And F translates to 1, 1, 1, 1. 8 translates to this as binary. And of course, then on the right side, we have all zeros. So what happened here was, because this one was in the MSB, it got copied over. And now the question is, hey, why does the CPU do this? And by the way, we are still discussing a very special case of signed numbers. Right shift, right shift operation as performed on a signed number where the MSB is 1 replicates the MSB. And the reason to that is it has to do with retaining the sign of the number. So, for example, if we had the number minus 128 in 8 bits, let's say. So let's actually do that experiment. And first, let me explain actually. Let's do it that way. So let's say we have what is this? 1, 2, 3, 4, 5, 6, 7, 8. Great. So a signed character, for example, is 8 bits. And let's say we took 1 and moved it by 7. It will come here. That represents a minus 128. Why? Because a 8-bit number, which is signed, a character, for example, the least value it can have is minus 128. Now, when I move it to the right by 1, we would expect that this number, minus 128, if we move things on the right, we divide them by 2. So for example, if I had a number which was 2, which is, well, 2, so something like this, if I moved it to the right by 1, this becomes a 1 because this 1 shifts here. So this is 1, this is 0, and this value essentially is 1. Similarly, if it was 1, 0, 0, I move it right by 1, then it becomes 1, 0. And 1, 0 is 2. So if you move the bit pattern to the right by 1, you divide by 2. If you move it to the left, you multiply by 2. Okay, and that rationale or that reasoning is very important, because if I were to move a number which represents the bit pattern that represents minus 128, if I move it to the right, then it should become minus 64, exactly half. And that can only happen if this is the bit pattern. Why? Because this represents minus 128, this represents 64, and when I add both of them, I get a negative 64. Similarly, if I were to shift this again by 1, I should get a negative 32, and that can only happen if I have minus 128 plus 1 plus 64 plus 32. And if you add all of these up, it becomes a minus 32. So this, by the way, is called the 2's complement form. And what happens is representing negative numbers becomes straightforward. You can do add, left shift and right shift, and because the sign bit is preserved, what happens is you get literally this effect of the number getting divided by 2. Now, there are 2 types of right shift at the assembly level. One is called the arithmetic right shift, and the other one is called the logical right shift. So what we have taken a look at in case of signed numbers, again, this only relates to right shifting. In case of signed numbers, when you move things to the right, the signed bit is preserved. And it is preserved just because the mathematics of division and multiplication makes sense. When we move to the right, divide by 2. When we move to the left, multiply by 2. So now you can also imagine that instead of multiplying a number by power of 2, like 2, 4, 8, instead of kind of activating the multiplier hardware, what can be done is you can simply shift bits and effectively achieve the multiplication by power of 2. So power is saved. And also, you don't have to activate a big circuit. It takes time to compute multiplication. So this is straightforward. In fact, you could multiply 3 by 5 by first multiplying 3 into 4, which is left shifting by 2. So 3 becomes a 12. And then you just add another 3 to it. So all multiplication and division can then be translated into shifts and adds, and shifts and subtract. So think about that. That is the advantage, speed advantage. That's why people have to learn these tricks because it makes computation easy. Okay, perfect. So we talked about the shift, and what we talked about the retention of the sign bit, that's called the arithmetic right shift. Now what's a logical right shift? Let's go and do a demo because I think demos are the best way to learn things. All right, so we are going to now, let's see, I'm going to copy this if I did this correctly and paste it. Yes, I did it correctly. What I'm going to now do is have unsigned int b equals to 1. So a is signed and b is unsigned. And all I'm going to do is change a to become b. Same exact thing. And let's see what happens. So compile, run. You see what happened here? Instead of being F8, and you see that there is a one less 0 here, which means there's a 0 on the left side of 8. So, there is, this can be read like so. So now you notice that this, instead of being F, it's 0. What that means is, in case of unsigned numbers, unsigned character, unsigned integer, unsigned anything, if you treat a register as if it's unsigned, then what happens is instead of replicating whatever was the MSB, that is not done. The replication is not done. Instead, the content gets moved to the right and zeros get padded. That's what happened here. So this is a very fundamental difference between signed numbers being moved to right and unsigned numbers being moved to right. So do remember this, and this is very critical. This is very, very important. A lot of people don't know about this. Then they make errors when trying to solve the competitive problems, or trying to solve DSA related questions. This is ultra important. You have to remember this. So yesterday we took a look at what bit manipulation means, what are the different types of bit manipulations, and today we explored only one specific thing about shifting bits left and right. And that has to do with the fact there's something called arithmetic right shift, where the MSB or sign bit is preserved and copied over as you move to right. And then there is something called logical right shift, where the MSB is not preserved. So you need to know this. You can go ahead and along the same lines practice more variations of the problems, play around a little bit. And what we'll do as part of our next video is start to look at things like what is masking, how do you flip bits, how do you use the XOR, ANDing, and ORing operation. We'll go through all of those step by step, and by the end of the series, you will be a master of bit manipulation, guaranteed. It would be very hard to make a mistake. All right, so with this, I'll see you in the next one.